Hello and welcome to this next lecture of computational chemistry. In the last lecture, we were considering matrix inversion. We defined the inverse of a matrix which involved cofactors as well as the determinant, and using that we worked out a strategy how to convert all the non-diagonal elements to 0 and how to make all the diagonal elements to 1 by dividing by the appropriate numbers in the diagonal values. And if some diagonal values were 0, we exchange that particular row by some row below that diagonal which has a large value in the diagonal term and replace it with the new row which is a non-zero in the diagonal. So, we were considering the program and we shall very soon consider that program also, but before I go into the program for matrix inversion, I want to describe another important topic which is called matrix diagonalization. So, in this process of matrix diagonalization, you convert a matrix, usually a symmetric matrix, n by n matrix, into its diagonal form. I shall illustrate that with a 2 by 2 case which I am considering in this example. Now, let us look at this example of matrix diagonalization. What this has is A is a matrix and X is a vector, X is a column vector. So, the matrix A multiplies the column vector and the result of that operation is nothing but lambda times that column vector. Okay. The equation is A x is equal to lambda x, that is my equation, or A x minus lambda x is equal to 0, that is my equation. This is called an eigenvalue equation. Okay. So, what is the meaning of this equation? X is some vector and when you multiply on the left of that vector, it is a column vector by matrix A. What you get is again that column vector multiplied by a constant. So, that means, if x was a vector in some direction, okay, the multiplication of a matrix gives you a multiple times the same vector. Okay. So, that means, multiplying by that matrix has not changed the direction of the vector. Okay. So, in general when you multiply by a matrix A onto a vector x, its direction also changes. Okay. So, this is a special case where the direction does not change. So, then the question would be, how many vectors are there which will not change directions when I multiply by the matrix A? It turns out that if A is an n by n matrix, there will be only n vectors like that. Okay? If A is a 10 by 10 matrix, there will be only 10 vectors, independent vectors, which will not change direction. Okay? So, therefore, these vectors are called eigenvectors and the values lambda are called eigenvalues. So, this particular problem is called an eigenvalue problem. So, what is the problem of matrix diagonalization? You find out all the diagonal values. The diagonal values are nothing but the different lambda values. Find all the lambda values which satisfy this equation. So, I can rewrite the same equation as A minus lambda I into x equal to 0. What did I do? I just, instead of, there is an A x. So, when I multiply this out, A into x, that is the first one, then the next one will be lambda into I into x. I is nothing but a unit matrix. So, whenever I have lambda x here, I can always insert a unit matrix in between because it will not change anything. Unit matrix can be inserted anywhere without any change of the product. So, this is 0. So, which means I have a matrix here A minus lambda I, this is a matrix that operates on x to give me 0. Now, there are only two possibilities, because on the right side I have 0, either x is 0, this is one possibility, or now the determinant of A minus lambda I, that has to be 0. So, if the determinant of this matrix is not 0, then what can I do? I can get the inverse of A minus lambda I. If I get the inverse of A minus lambda I multiply on the left by that inverse. So, that inverse into A minus lambda I will be 1, correct. So, 1 into x will be 0. So, then x has to be 0. So, that means, if the determinant of B is not 0, then I can get an inverse matrix, then it will force me to say that x will be identically 0. So, the only way this equation has a solution if the determinant of this is equal to 0. Okay. So, only for a 0 determinant there will be a no inverse matrix. So, I will get a non-trivial solution for the value of x. X is an eigenvector. Okay. So, now let us consider this determinant of A minus lambda I. What is this A minus lambda I? It will be an n by n matrix. So, if I have A minus lambda I, when I expand the determinant, so the determinant will be an nth order polynomial in lambda. It is an nth order polynomial in lambda. So, an nth order polynomial in lambda will have n roots. So, lambda will have n roots, and those n roots of this polynomial are called eigenvalues. Okay. So, once I know the eigenvalue by solving the polynomial equation, I can substitute that eigenvalue back here and get that A into x will be lambda into x. Once I know the lambda, I can satisfy this equation. Okay. So, therefore, once I know the eigenvalue lambda, I can know the eigenvector as well. So, this is what is illustrated in my next slide. So, we will illustrate this for a 2 by 2 case, which is a very easy case. So, once we understand the easy case, we can understand all complicated cases. All other things will be exactly similar, except the polynomial order will be larger, there will be more and more eigenvalues. Now, consider the details of a 2 by 2 case, that is what I have given here. So, this is a 2 by 2 matrix. What is my matrix? 1, minus 1, minus 1, 1. This is a 2 by 2 matrix. So, now I want to find the eigenvalues of that. What did we conclude from the previous slide? That the determinant of A minus lambda, that should be 0. So, what is A minus lambda? So, from this particular matrix, I have to subtract lambda from all the diagonal values. So, here there is an error here, it should not be A11 minus lambda, A12, A21, A22 minus lambda. So, this lambda is in the wrong place. Please make sure that this minus lambda comes in the second term here. Okay. So, what is my determinant? A11 minus lambda, A11 is 1. So, it is 1 minus lambda, minus 1 remains the same, A21 there is minus 1. So, there is no minus lambda here, this is not correct. So, this minus lambda should go on the second term. So, this is A22 minus lambda, my A22 is 1, this is A22 minus lambda, that is equal to 0. So, I have to calculate this determinant. How do I get this determinant? To get this determinant, suppose I have A, B, C, D. What is my determinant? A C minus B D. So, that is what I have given here. The first term in the determinant will be 1 minus lambda into 1 minus lambda. So, that is 1 minus lambda squared. So, what is 1 minus lambda square? Lambda square minus 2 lambda plus 1. This is 1 minus lambda square. Okay. And what is my second term? 1 minus lambda square minus this into this. So, minus 1 into minus 1 is plus 1. So, I have to take one more minus, because in the determinant is the product of these two values minus the product of these two values. So, since this is minus 1, so this is my equation, lambda square minus 2 lambda plus 1 minus 1. Okay. So, what is that now? This 1 and 1 cancels. So, it is lambda square minus 2 lambda, this is 0. So, when lambda square minus 2 lambda equal to 0, I can write it as lambda into lambda minus 2 equal to 0. This is the same as lambda square minus 2 lambda. So, what do we conclude from this? Now, this is written in terms of all the roots of that equation. So, this lambda is nothing but lambda minus 0. So, this product is lambda minus 2 into lambda minus 0, because when I say lambda, lambda is nothing but lambda minus 0. So, these are my two roots. Lambda minus 2 means lambda equal to 2 is a root, just lambda appearing, lambda equal to 0 is a root. So, this product implies that either lambda equal to 0 or lambda equal to 2. So, these are my two roots of my polynomial equation, and from what I concluded in the previous slide is that both these are eigenvalues. Now, I have to substitute these eigenvalues into my matrix to get the eigenvectors. That is what I shall do in the next slide. So, now I shall get the first eigenvector. So, to get the first eigenvector, what I do? I substitute lambda equal to lambda 1 equal to 0. Remember, I had two values of lambda. So, for the first eigenvector, I am going to substitute lambda 1 equal to 0. So, that is A11 minus lambda, A12, A21, A22 minus lambda. Here it is written correctly. Now, this into x, okay, A minus lambda x is equal to 0. So, when I multiply this, I should get 0 and 0. This is my product, 0 and 0, because this is a matrix A, it operates on a column vector. So, I will get a new column vector. What is my new column vector? This is a 0 column vector. Okay. So, now there is one special change I have made here. Remember earlier I have x1 and x2, that was there before. Now, why do I have it x11 and x21? Because there will be two eigenvalues, lambda 1 and lambda 2. For lambda 1, this is my eigenvector x11 and x21. This is my eigenvector for lambda 1. For lambda equal to lambda 2, I shall use it x21 and x22, because the second label in my column vector here represent which lambda it corresponds to. So, since there are several lambdas, I need the second particular column here. So, now let us multiply through this. Now, we know that lambda was identically 0. So, what is the rest of it? 1 minus 1 minus 1 1. This is my original matrix, lambda equal to 0, there is nothing to subtract. That into x11 and x21, that is equal to 0. So, how do I expand this now? This expansion is using the matrix multiplication. Okay. So, first row I multiply by the first column. So, what do I get? 1 into x11, this is my x11, then minus 1 into x21, this is minus x21, that is 0, because this particular row into this particular column is 0. So, this is my first equation. What is my second equation? Minus 1 into x11, 1 into x21, that is minus 1 into x11 plus x21 is equal to 0. So, these two equations I got by expanding and multiplying this matrix. Now, you see that both these equations are identical. Why are they identical? Because this is x11 minus x21 equal to 0. Just take the minus of that thing. Minus of this equation is minus x11 plus x21 equal to 0. Since both these are identical, the only solution to this is x11 equal to x12. This is my solution, because the sum is 0. So, once I know that x11 is equal to x12, okay, this is I call as the first eigenvector. So, I want to write the first eigenvector as a column now, x11 and x21. Now, I am taking this as 1 and 1. So, I am taking this as 1 and 1. Now, you will ask me, why am I taking 1 and 1, why I am not taking 2 and 2? It does not matter. If lambda is an eigenvalue, so if you multiply both by a constant, it does not change anything. The direction does not change by multiplying by a scalar. So, if lambda is an eigenvalue, I can multiply both sides by some lambda. So, it will not matter. So, I can take 1 and 1 as an acceptable solution. So, this is my first acceptable solution, 1 and 1. Okay. So, a multiple of this eigenvector is fine, okay, because since x11 equal to x12, 1 and 1 is okay, 100 and 100 is okay, million and million is okay. Only thing, it should be finite and it cannot be 0, because if it is 0 again, it does not mean anything. Okay. So, it should be either a non-negative number. Okay. So, that is my non-negative finite number. So, non-zero finite number. So, this is my first eigenvector. Now, how do I determine the second vector? Let me pause, give you time to think about it. So, instead of lambda equal to lambda 1, I have to substitute lambda equal to lambda 2. So, that is what I will do in the next slide. Now, look at this. For lambda 2, what is lambda 2? Lambda 2 was value 2. So, now I am going to subtract 2 from the diagonal terms, a11 minus lambda, a12, a21 minus lambda, a21 and a22 minus lambda. So, this is written correctly here, always subtract lambda from the diagonal values. So, when I substitute that, now I need a new eigenvector. What is my new eigenvector? x12 and x22. Remember, in the last case I wrote it x11 and x21, because that corresponded to the first eigenvalue. Now, since the second eigenvalue, I have given the second subscript, I have made it equal to 2. So, a minus lambda into a new eigenvector. Now, that again is equal to 0. Okay. So, now what I shall do in the matrix, I shall subtract minus 2 from the two diagonal terms. So, what is my new resulting matrix now? My new resulting matrix would be minus 1, minus 1, minus 1, minus 1. All 4 are minus 1. Okay. So, what is my equation now? Minus x12 minus x22 equal to 0, and from the second one also I get identically the same equation, minus x12 minus x22 equal to 0. So, what is the solution of this equation now? Solution of this equation is x12 is equal to minus x22. Since the minus x12 minus x22 equal to 0, one has to be minus of the other, then only the sum will be 0. So, what is my new eigenvector now? My new eigenvector is 1 and minus 1. So, I had two eigenvectors now. The first eigenvector was 1 and 1, the second eigenvector is 1 and minus 1. So, I can combine all the eigenvectors into a matrix of eigenvectors. So, since A was a 2 by 2 matrix, my matrix of eigenvectors is also a 2 by 2 matrix. If I had a 10 by 10 matrix A, my x also there will be 10 eigenvectors and 10 columns. So, I will have a 10 by 10 column matrix, 10 by 10 matrix of 10 eigenvectors. Now, we will introduce a new concept. Using these eigenvectors, I can multiply the matrix A in such a way that I get the diagonal value. So, that is my next slide now. Look at the next slide. So, what am I doing? Since I knew the matrix X, I can get the x inverse of the matrix X. So, how do I get the x inverse? You already know that the inverse values are cofactor of element A j I divided by determinant of A. So, what was my determinant of A? Go back and see. What was my determinant? 1 into minus 1 is minus 1 into minus 1. So, the determinant is minus 2. The determinant of this is minus 2. I shall use that to get inverse of x. So, what is the inverse of x? Half, half, half and minus half. This is the inverse of my matrix X. Now, how do you know that this is the inverse of matrix X? The best way to check is multiply x inverse into x. When you multiply x inverse to x, you should get identity matrix. Then only you know that it is inverse of x. So, what am I doing now? I am going to use a technique which is called a similarity transformation. I have obtained x, a matrix of eigenvectors. X inverse is the inverse of the matrix of eigenvectors. So, I shall multiply, this is my matrix A, I multiply on the left by x inverse and on the right by x. Okay. So, this is my x inverse A into x. When I do this particular product of these three matrices, what I get is 0, 2, 0, 0. So, what are these 0 and 2? These are nothing but my eigenvalues I started with. So, what we found here is that once I have a matrix of eigenvectors, I have an original matrix A. Again remember, I am taking a n by n matrix. I am taking an n by n matrix. I found its eigenvalues, I found its eigenvectors, found the eigenvector matrix x inverse A x. This is called a similarity transformation. Whenever I have a matrix A and I find its vector of matrix of eigenvectors, when I do the x inverse A x, it is called a similarity transformation. When you do a similarity transformation on any matrix, what you get is the diagonal values of the eigenvalues. All the diagonal values will be eigenvalues, off diagonal values will be 0. So, this means I have converted A into its diagonal form of the matrix using a similarity transformation. So, I have generalized it to any matrix of any size. Take a matrix A of any size, find its eigenvectors, find the eigenvector matrix, find the inverse of the eigenmatrix, x inverse A x will be A in the diagonal form. So, what is the diagonal form of a matrix? Diagonal form will be all the diagonal values will correspond to the eigenvalues of the matrix, all the off diagonal values will be 0, and once you have a diagonal matrix, it is very easy to calculate the determinant. The determinant of a diagonal matrix is nothing but the product of eigenvalues, the product of eigenvalues. Now, you will see that if the determinant of A is 10, the determinant of A diagonal also has to be 10, because it is multiplied by two matrices x and x inverse. So, if x has a determinant of value alpha, x inverse will have a determinant of 1 by alpha, because x inverse into x is 1. So, the determinant of x inverse will be 1 by determinant of x. So, automatically they will cancel. So, the determinant of A will be identically the determinant of A diagonal values. Okay. So, now what we can do? We can try to have a strategy to calculate the eigenvalues and eigenvector by some program. That is our next strategy. So, before I go to that, when I have an n by n matrix, the determinant of that n by n matrix, that is the determinant of A minus lambda I, can be written as a polynomial. It can be it is written as a polynomial of the nth power of lambda, because when I expand A minus lambda I and A is an n by n matrix, so nth power of lambda will occur. So, I have written that determinant now as a polynomial lambda to the n, b1 to the lambda n minus 1 all the way up to bn. So, this entire polynomial now, and this particular polynomial, this is the normal form in which you write a polynomial, but a polynomial can also be written in terms of its roots. Okay. So, a nth order polynomial can be written as a product of these functions. Which are these functions now? Lambda minus lambda 1, lambda minus lambda 2, lambda up to lambda minus lambda n. So, all these lambda 1, lambda 2, lambda n are all the roots of that equation. So, every polynomial equation of nth order can be written as a product of factors in which each root is contained. So, this is a very fundamental statement in your polynomial equations or algebra. So, a polynomial can be expressed as a product of the n roots of the polynomial, where each root is subtracted from variable lambda. So, these are my n roots, and for each eigenvalue now, which is the root, I can find the eigenvectors using exactly the procedure that I gave in the previous slide. I use exactly the same procedure, substitute the value of lambda, then A minus lambda x equal to 0, and I get relations between all the x's. When I get the relation between all the x's, I find the values of the eigenvector. Okay. So, next what we consider now, we will briefly consider how to write a program to calculate these eigenvalues. So, in the last class, we discussed a program for inverting the matrix. In this class, we want to discuss a program to get the largest eigenvalue. So, finding eigenvalues is a rather complex program. So, what we shall do? We shall just supply you with a good program to invert matrices, as well as a good program to find all the eigenvalues of a matrix. For the purpose of our class discussion, I will just find a procedure to find the largest eigenvalue. I will just outline steps to find the largest eigenvalue. Now, let us look at this. So, if A is a square matrix, it will have n distinct eigenvalues. So, suppose those n distinct values are such that I arrange them in a descending order, that is lambda 1, which is my first eigenvalue, suppose that is greater than lambda 2, which is greater than lambda 3, and which is greater than lambda n. So, all these lambdas are my eigenvalues. So, if such is the arrangement, let us see how this strategy for finding the eigenvalues works. As I mentioned already, these eigenvalues are arranged in a descending order. So, let me use the first eigenvalue equation, A V I is equal to lambda V I going from 1 to n. This is exactly the same as x. Earlier I had A x is equal to lambda x. Now, I am saying A V I is equal to gamma, it should be gamma I V I, okay. That is obvious, gamma I V I, which are all my eigenvalues. Now, all these V i's which are eigenvectors, since I had n eigenvalues, I will have these n eigenvectors, and one of the theorems of vectors and matrices says that all these eigenvectors corresponding to different eigenvalues, they are all linearly independent. What is the meaning of linearly independent? If I have an equation like this, I goes from 1 to n, C I V I, that is equal to 0 only if all the C i's are 0. So, if the vectors are linearly dependent, then all the C i's will not be equal to 0. Okay. See, for example, take this vector I and j in 2 dimensions. You know that in 2 dimensions, I can write any vector as some A I plus B j. Okay. So, if I want to get A I plus B j equal to 0, the only way this can be 0 is if both I and j are both A and B are 0. If the coefficients are not 0, I cannot get the sum of A I plus B j equal to 0. On the other hand, suppose I take I and 2i. This I and 2i are vectors in the same direction, let us say the x axis. So, if I have 2 vectors I and 2i, they are not linearly independent because one is just a multiple of the other. So, if I have 1 dimensions, only one vector is linearly independent. In 2 dimensions, only 2 vectors are linearly independent, and in 3 dimensions, you know that I, j, k, these are the 3 linearly independent vectors, unit vectors. In this case, they are not only linearly independent, they are also orthogonal. So, orthogonality is a very, very special case of linear independence. Linear independence is very, very general. Okay. So, what I have done now, A V I is equal to lambda V I, and next, since all the V I's are linearly independent, so the other theorem states that any vector x in that dimension can be represented as a linear combination of all the eigenvectors. It is just like in 3 dimensions, any vector in 3 dimensions can be represented as sum of product sum A I plus B j plus C k. Any vector in 3 dimension can be represented as a sum of these 3 I j k. So, similarly, any vector in n dimension can be written as a sum of product C 1 V 1 plus C 2 V 2 plus C n V n. Okay. So, these are my sum of these are the eigenvectors. Any vector is written as a sum of these eigenvectors. So, what I shall do now? I shall multiply A into x 0. So, what is A into x 0? What was x 0? X 0 was A 1 V 1 plus A 2 V 2 plus A n V n. So, A into x 0 will be C 1 A V 1, C 2 A V 2, C n A V n. Okay. So, this is my A x 0. Then I multiply A square into x 0. What is A square into x 0? So, first I got this gamma 1 V 1, gamma 2 V 2. How did I get gamma 1 V 1? A multiplying V 1 will give me gamma 1 V 1. A multiplying V 2 give me gamma 2 V 2, second eigenvector, second eigenvalue. So, now I multiply A by the second time. When I multiply second time, I get gamma 1 square V 1, gamma 2 square V 2, gamma n square V n. Okay. So, when you multiply kth times, so I will get C 1 gamma 1 to the k V 1, C 2 gamma 1 to the k V 2 and C n gamma n to the k V n. This n should be actually be 2 here because it is a square. So, I can now take this gamma 1 outside. So, gamma 1 to the power k C 1 V 1, C 2 into gamma 2 by gamma 1 to the k. Why is it dividing by this? Because I have taken gamma 1 to the k outside. So, when I multiply through, I have gamma 2 to the k. Okay. So, now as k becomes large, and since gamma 1 is the largest eigenvalue, all these other terms will become smaller and smaller and go to 0, and only the first term will contribute. That is what I have shown here. Now, you see, as k becomes very, very large, okay, only the first term will remain. So, my gamma 1 will be a k plus 1 x naught I into a k x naught I. Okay. So, that is how my gamma 1 can be calculated. What is the strategy? Simple strategy, multiply A many times. When I multiply k times, only the first term will dominate, all the others will go to 0 because gamma n by gamma 1 is very, very small because gamma 1 is the largest eigenvalue. So, that is my strategy. So, I will briefly summarize the strategy and we will actually use this in the program. Okay, I am going to find an eigenvalue by taking powers of my matrix A multiplying on some vector x 0. Okay. So, what is my x 0 now? Let my x 0 be 1, x 2 0, x 3 0 and so on, this some eigenvector. So, I multiply A 1 times, this is what I got. Okay. Then what I do? I multiply 2 times, 3 times, so on, this is my algorithm. Okay. So, let me just summarize what is my final result. We will actually do the program in this. Okay. A into x k minus 1 is y k, x k is 1 by y 1 k into y k. So, basically I get my gamma I and V 1 by multiplying A repeated number of times. So, what I shall do? Okay, I shall keep each one slide so that you can see this. Okay. This slide I have shown you for a sufficient time. Now, let me go to the next slide. I shall display for sufficient time. I am multiplying A many times. I am taking out this mi's below. Okay. So, just look at this slide. I will show the next slide for some more time. Okay. I have defined these yks. Yks are 1 by mk up to m1 ak plus 1 x naught. Okay. It is gamma 1 to the k plus 1 c 1 v 1, and so finally I get xk. Okay. Now, if xk does not change anymore, that means I have a converged result. Okay. That is my next slide. So, if xk plus 1 is the same as xk, I have found the final result. So, what I shall do? We shall just execute this program fully, so that you will know how to get the largest eigenvalue. Okay. So, in the next class what I will do? I will consider the matrix inversion program as well as a matrix diagonalization program, which diagonalizes only the largest value, which you get, which we give, using which we get the largest value. To get all the values is not trivial. So, what we will do? We will take an established program from some source and use it for our purpose. But as far as our course is concerned, you should know how to invert a matrix and you should know how to get the largest eigenvalue of the matrix, and you should know all the concept related to eigenvalues and eigenvectors. I will conclude here. Thank you.